Dear Sir, Madams, before starting I would like to thank all the members of organizing community of this conference to give me the opportunity to present the result of this work and to light design and characterization of microtubes based on tin oxide and aluminum doped tin oxide for gas detection application. The plan of this presentation is as follows. First, we start with an introduction in which we present some general information on metal oxide gas sensors and objective of this work. Secondly, we present the result of preparation and characterization of microtubes of tin oxide and aluminum doped tin oxide. Then we present the result of sensor fabrication and characterization based on prepared microtubes. And finally, we end by conclusion. So, since many decades, the world awareness about environmental problems and human safety is increasing with the technological developments. So, gas sensors are therefore required for many applications. Among this field of application, we can mention industry sector, agriculture sector, detection of toxic gas, and biomedical sector. A sensor is a device that receives a stimulus and transform it into a usable physical quantity. The response of this type of sensor is due to chemical interaction between the gas molecules and the sensitive layer of the sensor. Among this type of metal oxide gas sensor, we can mention piezoelectric sensors, optical sensors, resistive sensors. This type of sensor suffer from a lack of sensitivity, selectivity, and very long response time. So the objective of this work is to realize a resistive gas sensor based on tin oxide microtubes and improve these properties by doping effect. In general, sensors consist of a sensitive layer deposited on a substrate on which contact electrodes are deposited, as you can see in the following figure. Regarding the metrological characteristics of the sensors, we mention sensitivity, response, selectivity, response time, recovery time, and lifetime. The fabrication of our sensors goes through two steps: preparation of microtubes and deposition of microtubes on a micro detection platform. The tin oxide microtubes were prepared on three steps: preparation of solution, formation of tin oxide fibers, and thermal treatment. The solution was prepared by dissolving tin chloride dihydride in a mixture of DMF and ethanol under magnetic stirring for 30 minutes. Subsequently, PVP was added, followed by stirring for 3 hours at room temperature. A force spinning system has been designed and fabricated in the LITSIM-P laboratory from the preparation of metal oxide tubes. It based on a stainless steel rotating reservoir with two symmetrical nozzles, surrounded with collecting metallic bars for allowing fibers collection during jet process. The solution prepared was poured inside the spinneret and ejected onto the collector and transformed into fine fibers due to stretching and induced by centrifugal force and evaporation of the solvent. In order to select the adequate annealing temperature to remove PVP and solvent, TGA analyses were performed. We can see here in this graph that temperature at which this element are removed is 600 degrees. So the fiber were annealed at 600 degrees with a heating rate of 5 degrees per minute for 5 hours. The characterization technique used are X-ray diffraction and scanning electron microscopy. X-ray diffraction analysis shows that the structure of our samples are tetragonal rutile characteristics of tin oxide. You can see here that the grain size decreases with increasing the aluminum concentration. Scanning electron microscope analysis show that the samples are formed of double-wide microtubes, and it can be clearly observed that the average diameter of annealed dropped after annealing due to the removed of the PVP polymer and solvent. We can see also in this slide that the average diameter of microtubes decrease with increasing aluminum concentration. To complete the scanning electron microscope analysis, an EDS analysis were realized to explore the chemical composition of our samples, which showed the presence of main elements tin and oxygen and aluminum with impurities like zinc and copper. To fabricate our sensors, we place the synthesized microtubes on a micro platform of detection with interdigitated gold electrode separated by 10 micrometer. To characterize the response of gas sensor, the sensors are placed in characterization circuit, which consists of a dry air generator, flow regulator, gas chamber, card Arduino, controlled at LabVIEW interface. Sensor response against gas was studied measuring the resistance of device using a voltage dividing circuit, and to activate the sensor response, the thermoactivation mode is used, as you can see in this picture. The prepared sensor based on microtube of n-doped tin oxide and tin oxide doped with 6% of aluminum. The following figure presents the characterization result of our sensor and under ethanol, acetone, and benzene at 180 degrees. We observe that there is an improvement of the response and the response time by doping effect, and that the sensor based on tin oxide microtubes doped with 6% of aluminum has a high sensitivity to ethanol and acetone compared to the other sensor, and also has a low sensitivity to benzene. To improve the characteristics, we increased the activation temperature to 250 degrees. We observe that there is an improvement in the response and the response time of our sensor by temperature effect, and that the sensor based on n-doped tin oxide microtubes has a high sensitivity to ethanol compared to the doped sensor, and the doped sensor has a low sensitivity to benzene. Another study was done to investigate the effect of flow. We increase the flow rate from 50 SCCM to 200 SCCM. We also observe an improvement in the response and the response time due to the flow rate effect. Finally, in this presentation, we have given some general information on metal oxide gas sensors, indoped and different aluminum doped are successfully synthesized by force spinning technique, which is a simple and safer technique with a high production rate and faster than other technique, as confirmed by scanning electron microscopy. The characterization of our sample of our samples by X-ray diffraction and ADS show good structural properties and confirm the successful substitutional doping of aluminum in the tin oxide lattice. The sensor characteristics of n-doped tin oxide and aluminum doped tin oxide highlighted the effect of doping on the improvement of the sensor sensitivity, response speed, and partial selectivity. The optimal working condition is condition of the sensor, such as activation temperature and flow rate were respectively set to 250 degrees and 200 SCM. Thank you for your attention.